it's a very nice hike. Okay, it's unlike any sort of a hikes you've done before. Okay. So without further ado, I think I'm going to yield the floor to Ferdinand.
Yeah. Well, thank you again. And actually, I'm really sorry for my lecture yesterday. I got out of flow, and hopefully today it works better. So we have talked about all these common vibration modes. We know how ions are trapped and so on. And the question is now, what do you do with them? Okay. In the lecture 2, we deal with the motional degrees and the spin degrees of freedom. We couple them. Okay. And that leads to some effects like this machine operation or the spin-dependent heat transfer. And the spin-dependent heat transport, that is something that I wanted to do, but actually Hartmut Heffner from Berkeley did it much nicer, so I will present his measurements. And then in the last lecture, we will get rid of these motional degrees of freedom. We will just use them intermediately, but mostly we are using it like a quantum computer, where we're dealing only with spins, and the motions are just there to make the spins interact, as I explained. So this is still spin and motion involved in the physics, and here only spins are involved, but we have more spins. Okay, good. So that is Hartmut from Berkeley, and the first thing he did was energy transfer through an ion crystal. So what happens if you transfer energy through an ion crystal? You can excite this ion with a blue sideband. That means you put a phonon into this ion, but it is coupled to all these other ions. It is a common mode for vibration. You cannot just think of this as an individual oscillation. It has you can decompose this oscillation into all the eigenmodes of the whole system. And then, of course, somehow you will see that this ion is also oscillating. So it is hitting the string at some point and generating all the superposition of eigenmodes, which are then shown here. And that's what we did. So you have this, you pick this first ion, and then there is a sort of springs here, which couples all of them. You excite this with a sideband. You can also do it with a pyro-2 pulse, that you have really a superposition of being kicked and not kicked. And then the superposition will be transferred to the other side. So he had no sensor at the other side. What he did, he looked when this comes back again. It propagates and comes back somehow. After some wait time, you can analyze what happens with the motion. Okay. And that is now what you see as a function of wait time. The visibility of this so-called Ramsey pattern. You do a pivot pulse, then you wait, then you do another pivot pulse, and you go up states. But you see it is not going full up because the propagation went all the way to and back. And then depending on the wait time, you see some oscillations. And these oscillations look interesting, okay, but indeed they are not so interesting because it's just a decomposition of this excitation here in terms of all these common modes of vibration and seeing all this in superpositions appearing. So it is a system which shows that you can put this superposition in a large crystal. So that's always kind of propagating all through the thing, even though these other ions have oscillations on them. And this is remarkable, I think. But on the other hand, it's linear dynamics. It's a superposition of all these eigenmodes, and that's not a big deal for quantum simulation. It can be described efficiently. So how can you do better? And that is spin-dependent heat transport. Okay, spin-dependent heat transport is now something which is really important because people conjecture that this has to do also with a lot of biological systems where energy transport is important. Because you have here some spins, okay, and the energy transport from one to the other side is the phonons, and this is depending on the situation of the spins. Okay, so now the spin, they can be modeled that you have a hopping of energy from one to the other side, yeah, in a spin-dependent fashion. But here, all the energies are equal. In reality, they are not, okay? there's a blocking because this energy cannot go to this because there the spacing is different and so on. So there is a lot of inhibition because the spin systems have not exactly the same energy. But maybe you can still have an energy transport if you couple these spins now to a phonon bath here. So now you have a spin boson system, which is coupled, but this energy mismatch is kind of cured by different oscillator states here. So here, this one has a high splitting, so you would like to have a little bit of oscillation only, but this has a low splitting, but maybe you can cure it by putting more phonons in, and then you can resonate the channel here. So that's the idea how this resonance condition can be vibration assisted, okay? And that's the idea to make now an experiment which shows this in a nutshell. And here, more mathematics. If you try to cast it in a Hamiltonian, you have to think of this hopping. Okay, this is the hopping between two sides. Yeah, this hopping J, that the excitation goes to the next side here from E to J. And then you have some spin motion coupling. This is the spin coupled to the motion. That's exactly this arrow, which is K. So each one it can be individually different, okay? And then you have maybe some detuning here, which illustrates that this here is larger than this. So that is the detuning of all these kind of different sides, okay? And this is now a huge Hilbert space. The spin boson model, even with a couple of sides, becomes really explosively large because you have, say, go up to 4 quantum, n equals 4, 5 quantum level, spin 1/2, then you have already on a relatively small system, an enormously large Hilbert space. So that makes sense to simulate this. But now, sorry for the next transparency, you see only 2 sides, okay? So the beauty is limited, but still it's a very important experiment. I like it very much. What Hartmut did, he took 2 calcium ions, he made an interaction, a spin interaction. I told you how the spin interaction is working. This is kind of a gate between these 2 ions, okay, with this coupling strength J. But then one is detuned, one has a different energy splitting, so this cannot happen, it's off resonant. But the spin motion coupling can cure this, okay? And then you have all these different components, but now only for 2 sides, yeah? And you can do now individually the time evolution of each of these Hamiltonian thing individually, okay? The detuning, these are off-resonant Rabi oscillation. They don't have large contrast, but they are oscillating fast. That's this part, AC Stark shift, so to say. This is the spin motion coupling. It's this red sideband excitation. And this is the spin-spin coupling, how the energy would flow back and forth if they are not detuned, okay? And now you switch on.
Question.
Yeah.
So your phonon bath is inhomogeneous, right? And do you consider correlation?
Well, I think here it is, yeah, here it is, each of these ions has its own, in reality, should have its own phonon bath. I think there are many different modes where the ions participate. And if you look in reality, actually, the eigenmodes are different. The eigenvectors are different on different locations of an eigen. So it becomes super complicated. But you have to think of this as to each ion, some say reading mode. Okay, this is oscillating like this. Now take the next one. You have one ion in the middle, which is not oscillating. The other ones are reading. So this would be attached to no phonons of this mode. So it is really according to the eigenvectors of this crystal mode, that's how it happens. Okay, it is. This is way more simple. Yeah, but in reality, I think each ion has different access to all these common modes, and to each one a different one. Okay, so in principle, I could calculate it, but it's becoming complicated. That's why these K's are here all different, okay? They're all different. For all the modes E, there are different Ks for different sites J. Yeah? So that's the reason for this, that you have this complex eigenmode structure. Okay, but here we are more simple. We have just two ions. This is way more simple, okay? And what he does now is this experiment. He prepares the ions not in the ground state, okay? This is important. Not in the ground state. You won't have some phonons, okay? If you cool them all down to ground state, well, then you should not start this thing because it cannot vibration resistant. You can do also sideband cooling, but you don't necessarily need to do it. You can do it, you don't need it. Now you put some excitation into the system and you turn on all these Hamiltonian parts in one moment, okay? That's the simulation. So the spin, this one, this one, this one, this one. Everybody is turned on for a certain duration, and then you look whether the energy went from the ion number 1 to the ion number 2, okay? Whether this happened, whether this acceptor really took the energy from the other one. And that can be read out by ion fluorescence. And that's the result. So this is this effective detuning of the laser. And here on this side, we have the negative detuning. And that means here the environment absorbs energy. On the other side, the environment gives up energy. And it is happening on both sides. That means you can have energy transfer even though you have a different detuning, okay? So this detuning is small here and large here, and if you go to this side, it's exactly opposite, okay? So you tune this one over the resonance. Here you are perfectly tuned. There it would work, the energy transfer without phonons, but here it would not work, and here it would not work. Here you can give away phonons. Here you have to pick up phonons from the environment to make it work. And how can you show that it's really like this? You can now cool the ions to the ground state, okay? Now you cool to the ground state, or not exactly, but you cool them much closer to the ground state. And now it is very hard to get some energy from the environment because there is none, okay? And that means you are getting here no transfer to this side. Yes?
I'd expect if there were zero detuning, then the ions wouldn't need the environment, so they just would exchange energy. And if there is a detuning, then they can take advantage of the environment to do maybe as well. But the probability of transfer is very low when the detuning is zero. How come?
Yeah, this is why this is here so small. Okay. Yeah. Well, oh sorry. Let's go to this Hamiltonian. So this is a small part of this. This detuning is in that moment is 0. So this part is 0. So we have to go through numbers, I guess, to understand this and really look how this J with 1.3 kilohertz acts over a duration. I don't know exactly how long this was, but that is kind of looking into the numbers and well, I can just assume that this is a kind of a theory curve here. And well, sorry, but I think that comes out of this model. It's not something peculiar. It has to do with the time you run the simulation. If you run it longer, everything goes up. But we have seen a little bit of this already in this individual part. You see, here you see it can go up quite high, okay? Can go up high if you have the right time to do it. So that's, I cannot say more, okay? Okay, this is now spin-dependent heat transfer. Now switching gears completely, this is now the single ion heat engine, which got so much publicity, and I don't know quite why, but it is the first time a single ion does this work engine, and it is really a single ion heat engine, which is working like this. You have you start with step 1. You have some wave packet. I will explain this more in detail. The wave packet here, that's the wave packet size. And now you can compress the volume, okay? You can compress the volume by changing the trap potential from this to a deeper form, okay? This is a cold wave packet. You can now make the wave packet hot. A hot wave packet means you heat up, you put some heat into the system, you heat really the wave packet up, it becomes a broader wave packet, and the broader wave packet is then a hot one. This hot one evolves in this potential and expands, okay? And then we can expand this potential shape again, and then the large wave packet is the last step cooled to get a narrow wave packet, a cold one. Okay, that is the cycle of the auto engine. And I don't know in more detail, how do we do it? So we have the radial vibrational degrees of freedom. In this direction, we have the axial degrees of freedom. Okay, and what we do, we form a very special trap. Nobody wants to have a trap like this in reality. Okay, that is the only trap in the world which has this by purpose. Some people build it, unfortunately, they have not a good alignment of these radio frequency bars. And that means the potential in radial direction is less stiff here than it is here. So what happens? Here you have this potential which is kind of relaxed, and here it is stiff. So if you move the ion in this direction, you come from a stiff to a shallow potential. Okay, you can vary this by just varying the position here. So what is now the purpose of this engine? You can have a heating and a cooling in the radial direction, and that induces an axial displacement. That's what we are going for. Because, just to say this, a broad wave packet, a hot wave packet, will feel this force of the radial direction much more. That means it will accumulate here easier. However, if the wave packet is narrow and small and cold, it likes to sit also here. So you can heat it, it will go to this side. You can cool it, it will go to this side. So it goes back and forth. If you heat and cool it at the right driving, then you will start to make it oscillate this way. Okay? So that's what we are going to do now. Heat it, it moves, it becomes wider, and then it moves. And then we cool it, it goes back. So it moves, and then you can cool it, and it goes back. So the wave packet does this circle here, heating, then moving, then cooling, then moving back. Okay, and so you have to do heating, cooling, in a very fast sequence. That is the challenge here, because this axial motion is in the range of a little bit less than a few hundred kilohertz. So you have to really fast cooling and heating, otherwise it doesn't work. And you do this driving exactly in resonance with the axial track frequency, because then you resonantly enhance the process. And this is now the theory that's the theory how this compression value omega-1 and omega-2, omega-1, omega-2, that is giving you this kind of compression value, and that determines how this frequency is changing and how the temperature is changing. And that then gets you the area here under this, and that's the delivered work. Okay, and that's the theory about it and the proposal, and then we realized it. And you see here the sketch of the trap with these bars which are tilted back to this z-axis, yeah. So in that axis that you have here a radial shallow, a weaker potential than you have here. There is, how do you do cooling? Cooling you do with laser light. How do you do heating? You could also heat with laser light. It's, however, much harder. And we did it the easy way. We periodically put some noise noise on these electrodes. And the noise is coming from electrons which are in this direction. That means the noise is going radial, makes radial noise, not axial noise. Okay?
Ferdinand,
Yeah,
question, a naive theorist question.
yeah.
So I imagine that as you cool these down, their probability, there's some finite height of your track, right?
Yes.
So do you have to cool them down? Does the finite but non-zero probability, small but non-zero probability that they tunnel out of the track, do you have to increase the height of your track?
So the rate at which the energy of the ion is in range, we will see in the range of less than 100 milliamp. That's energies in the milliamp version. And the that which we are losing has some electron volt there. So it, I don't know, actually, it is really, I think, 5 orders of magnitude higher than other. So we'll never see that is really, it is different to the neutral atoms where the potential wells are steep but not so deep. Okay, so they can have a high omega, but still they end very deep. In the trapped ions, you have a super deep potential also. It's not only steep but also very deep. And so you can act harmonically over an extremely large range of phonon numbers.
Was your noise thermal noise with an effective temperature?
That comes in a moment, the temperature, yeah. So the cooling is done by laser light, and the heating is done by periodically switching on, and we do this really on these electrodes in order to heat only one radial mode. So that is complicated, but you need to make noise here on these opposite electrodes, such that this mode is kind of motionally excited by putting electric noise on the ion. Okay, and then we have to observe from the side on this ion and look whether it's really oscillating back and forth. Okay, we have to check this with a camera system. And we have to stroboscopically look on the ion that is really moving, okay, because it's moving very fast. If we take a slow camera, you just see a smeared out picture. That's not what you want. What really the points at the function of time. And this is now continuous laser cooling. I see that mimics a cold bath, and this electric noise in radio mimics a hot bath. And you can say, okay, this is an electric noise, it's deterministic, it's not a temperature. Well, that's right. But you have, on top of this, you have some dephasing due to the cooling. So you overwhelmingly make much more noise than cooling. But the spontaneous cooling events, they dephase this noise. So it is somehow still a hot bath. Yeah, it's maybe not the ideal hot bath because it's, well, this noise is deterministic, yeah, so it is kicking the ion back and forth in some fashion, but it is. So that is the time sequence, heating, cooling, and so on. We have to make this very fast and resonant with the axial motion. And that leads then to a visible movement of the ions. This is stroboscopically taken, so a very fast camera where you gauge at certain windows with respect to your driving. So you know when the axial frequency is coming, so you know exactly the axial motion, and then you are triggering, you're opening the detector here for very small gate times and taking a lot of pictures, accumulate them on the chip, and you see this is really moving back and forth. Okay, that is beautiful, that it's working, and now we can characterize how good it is working. So here is the relative trap frequency. How do we determine this? Well, we know the position of the ion from the camera pictures, and if we have a displacement of such and such micrometer, let's say it goes 5 micrometers to the side, we know, okay, with this taper, we get a little bit lower frequency or a little bit higher frequency. So that is measured from the position, and this here, the relative mean phonon number, that's measured from temperature measurements of the ion at different points of time during the driving. So you see, this doesn't resemble too much our original Otto cycle. It's what Ronnie said, it's going completely, well, it is in principle these 4 steps, but they are all kind of mixed into each other. And we try to get this area. In reality, it would be a much larger rectangle, and we just get a leftover of a little bit of this, so to say, because all the corners are taken away. Yeah, and that reduces the efficiency also a lot. Yeah, because it doesn't follow here. The steps are merging into each other. Yeah, so and then we can get the efficiency from the heat engine, and we see that this depends quadratically on the temperature. That's what you would expect, that the output power goes quadratically with this delta T. That is the difference on the hot and the cold reservoir, so to say.
How do you read the mean Phonon number?
Yeah, the mean Phonon number is coming from the temperature measurement. I've taken it out, but we take spectra of the ion at different positions of time. So it is also a challenge to measure the temperature so quickly that you can measure in situ while the circle is done. So that is not easy. Yeah,
That's a spectroscopic measurement.
it's a spectroscopic measurement. We look to narrow lines and they broaden if we get a higher temperature. And we look for the broadening. We have done some calibration first and know what is the broadening corresponding to what temperature. And then we can look to this broadening. It's an EIT temperature measurement which we applied here. And we had other type of measurements because that is typically not that you have so little time to measure the temperature in a cycle, so to say. It is not so easy. Yeah? So to determine this and determine this, we did a lot of checks and tests. So that is, you see the error bars are also pretty large here. In this direction, they are very small because we know exactly where the position is, but the temperature measurement is much higher. And then we cast it in the Phonon number. And you see here, there are plenty of phonons. So it has nothing to do with quantum levels, okay? There are hundreds of phonons and the displacements are micrometers, so it is way larger than any wave size, okay? So that's why I say it is fully classical engine. You say no, not the slightest amount of quantum effects here. And so that is what the reason why we wanted to go a step further. And we wanted to make this engine now fueled by different sort of fuel. The fuel is now the spin. The fuel is now the spin of an ion. So we are approaching our spin engines kind of in steps, but we still deliver into some motion. Okay, that's the motional degrees of freedom. And this is a spin-driven engine. And this is in collaboration with our friends from Dublin here. And that's our team here. So now, before we had the radial motion is heated and cooled, and that generates work in the axial motion. Now we are getting rid of this radial mode at all. We don't need this any longer. And the working medium is now the spin, our spin 1/2 system. And the thermal bath is exactly how do we populate this spin up and spin down, like an NMR temperature. Okay, this is how we generate the cooling and the heating. And we like this so much more as compared to heating a radial or an axial mode. Because the spin temperature we can determine so accurately, it is much easier to handle our spin than a radial mode. Yeah, this is a big advantage to have the spin as a working medium, because you can control it so nicely. So all spin down is temperature 0. A complete inchoate mixture of an up and down in Bloch sphere, it's an arrow of 0 length at the center. That is the infinite temperature, and we can switch from this low and high temperature by controlling the optical power. And then we need a different gear mechanism. Now we can no longer trust on this coupling between radial and axial modes with the taper, but we use now a spin-dependent optical dipole force. So that is now acting on spin up and spin down in a very different fashion, kicking spin up to the right-hand side, kicking spin down to the left-hand side. So if you have a spin imbalance, it will be kicked to one side predominantly, okay? And if you have a very high temperature, it will not be kicked in average because it is spin up and spin down, and so where should it go? So that is now this optical force, which makes the spin be kicked in the axial direction. And then we can deliver work really in sort of different quanta. Now we are approaching really a quantum regime because we can count now these phonons here, one by one, okay? So again, heat engine here, and that is done. This is the thermal state. The probabilities here we can control by optical pumping. And that is our Zeeman splitting is basically, this is the temperature versus probability. So as I said, if everything is super cold, we have this arrow pointing here. And so, and optical pumping brings us to this state. So we just switch the sigma laser on and pump out of the spin up state into spin down. Then we get everybody here. Well, perfect. And we can also put kind of bad optical pumping. Okay, then you have some distribution, some light goes up here and brings it here, some brings it down, and you can really control this light polarization so accurately that you get every type of temperature very quickly. This optical pumping also has the advantage that it's going very fast. You need only a few cycles of optical, and this is 7 nanoseconds. So in I don't know, 20 nanoseconds, you can be done with optical pumping. That is very different to heating. Okay, but still, it means we have to go from the spin up probability in steps up and down, and you see effectively this is changing the temperature according to this definition of temperature between a cold and a hot situation. Yeah, and that goes pretty fast because we have to be again in the resonant to the axial motion. But you see this duration can be fast and we can very quickly switch our temperature of the. And now we need the gear. The gear is now, we have this single ion in the harmonic potential, but on top of it, we have a spin-dependent potential, and that is an optical standing wave of limb per limb, as I showed you last time. And this induces an AC Stark shift depending on the spin of the ion. And this AC Stark shift is really high. So we have 2.7 megahertz modulation on top of this. And if you are spin up, you would be kicked this way. If you are spin down, you would be kicked this way, okay? To the left and to the right. Now, please note, this only works if this slope is going down and this slope is going down this way. If you are moving the standing wave by only 200 nanometer, the whole thing is over. So we have stabilized our ion into this node of the standing wave. This is challenging as an experimental technique to get phase stable light, which is phase stable with respect to the wave packet of the ion. And if you go to this paper here, we have described how we can stabilize the phases of light with respect to the wave packet by 6 nanometer. Okay, so you have to think this standing wave is now really fixed in space with the ion position. The ion position is of course given by this harmonic center here, and we can fix it to 6 nanometer. So 6 nanometer is small as compared to this modulation.
How delocalizes the wave packet of the ion? How delocalizes the ion wave packet?
The ion wave packet is localized in the trap and by cooling, and the size of the wave packet is about 15 nanometer, but we can stabilize the standing wave to a fraction of this. Yeah. So, yeah, I don't know, 1.4 megahertz and calcium, maybe it's 20 nanometer. I don't remind myself perfectly. Okay, we have now the gearbox, and we shine light, as I showed you, cold bath and then hot, cold, hot, cold, hot, as a time sequence on this ion. And when it's hot, it doesn't know where to go, and when it's cold, yes, then it knows it gets kicked to this side, okay? So it will, if this is in the frame of the axial frequency, it will start oscillating back and forth after a while, and that's what we will observe.
So Ferdinand, is the 280 nanometers, that's the wavelength of the excitation?
No, that is just the standing wave pattern. It depends on the angle. We are going on 45 degrees, and there is an optical lattice formed from these two Raman beams. Okay, but the Raman beams are not exactly opposite. It's length per beam, but then there's an angle. Okay, and this is the effective length of this. The light we use is 397 nanometer, but as they are at an angle, it's not perfectly lambda over 2.
And why do you choose 280 as the spacing?
Well, we didn't choose it. We have these optical ports at 45 degrees, and we have the wavelength, which is resonant to our S2P transition or off resonant, but uses this light source in this light transition. So we are fixed with the wavelength 397. We are fixed with the angles because our laser beams impinge the ion under this angle, and then we get this 200. Just the result of this. Okay. Not that we love it. Okay. If it would be 300, we would be also happy.
And you can
Okay.
change the angle, though, so that
Pardon?
gives you changing the angle. would be
Yeah, exactly. So if blue light, here's one Raman beam and one, that's the other, two, and that forms this, no, sorry. This pattern, okay? And here the spacing is now 200. Yeah. Okay, so going on. Now this is the sequence. We sideband cool. We want to have the ion initialized in 0 phonons. Then we do the optical pumping to get the spin first into spin down, okay? And then we put this alternating optical pumping. So we basically switch between cold and hot reservoirs with a laser periodically while we have this optical dipole force on. That means the standing wave is switched on here. And then we change we vary how long do we do the heat engine operation. So if we just stop here, it's a very short operation. We don't expect that too much happens. And we increase this and see how the motor starts and how it evolves. There's no friction force, so it will just start an engine, and as it doesn't dissipate to something, the oscillation becomes larger and larger. And I will talk about this, what happens when it becomes too large. And then, so this is, again, in this 4-stroke unit, you can think of here, the ion is oscillating, picks up oscillation, and when it's in the spin up down increment mixture, it doesn't know where to go, but if it spin down, it knows exactly I want to go down this slope, the blue slope. Okay, so that is the Otto cycle, and here is the spin dependent force which drives it, or which is the gearbox, and the pumping is the heat you put in. So now we have to analyze what happened. We have to check what is the phonon distribution after some operation time of the heat engine. And how do we do it? First, we do optical pump. That means we get the spin back to spin down. And then we do an electric kick. Okay, that's just for analysis. Think of the phase space. The phase space is X and P. And we are now, say the engine brought us here. Okay, here we are. Yeah. This is our place where a certain duration of engine brought us. And how can we check now what is this state in phase space? What we do an electric kick with some amplitude and phase and check whether we are in the ground state. And you could see, well, this didn't work. Okay, so we vary our phase and check whether we come to the ground state. This is about the ground state. We vary the phase, and then we see here is the ground state. Now we know in reverse that we are here, because this electric kick brought us to the ground state, so we know we have to be here after the wave cycles. So that is this displacement which we do to bring it back, okay? To bring it back into the ground state. And why do we bring it back into the ground state? Because that has a very beautiful optical signature. As I told you last time, the red sideband on the blue, on the ground state does not happen, because there is no n equals -1. So if we are in the ground state, we can do a red sideband excitation, and we don't excite the ion spin. We don't go to the upper state. When, however, we have some phonon number here, we get to the excited state. The ion becomes dark. The ion doesn't become dark if we are in the ground state. So we have an optical signature of, well, only if there's some motion left, we can excite it. If there's no motion left, it cannot be transferred. And this is formalized in this Q function, where you have this displacement that was the displacement D on the state, and then looking to the overlap with the state n equals 0. Okay, and this is a very nice way to measure it. Okay, and now what happened? This is now the Q function measured for different durations of the heat engine. Here it didn't work. The heat engine was only switched on for 0 time. So we have the initial wave packet. We measured this. You see, this is the angle, and that's the amplitude. If we run it for a short time, we see already a little bit of displacement out of the center. If we run it longer, we see more displacement. What we see now that this becomes really displaced, but also squeezed. And the longer we run it, the more it becomes squeezed. Okay. So now we can describe this Q function. We take a model, we take the displacement, we take the squeezing, and then also the overall broadening is described by a thermal distribution. So we have all the 3 components in the Q function, and we describe it and make a wave packet out of it, so to say. And now we can look what happens with these different terms. From this displacement, the squeezing, and the average phonon number, the mean thermal phonon number, we get this. What is the work that we have done? Okay, the work is now something you can extract plus something you cannot extract, because an average phonon number, a thermal one, doesn't help you. Okay, so only this part you can extract. And this part has to do with a coherent push on this, so how much was displaced. And then the squeezing also can be used. And here now we plot for different durations of the heat engines to run. We plot this extractable work, the red points, and the energy, the black points. Well, that's what we find. And we find it becomes larger and larger. Now, why doesn't we run it further? The problem is, you have seen this gear works only over a range of 280 nanometers. If the excursion becomes comparable to this range, then the gearbox doesn't work any longer, then the displacement becomes negative, and then if you come to this end, then this is also the reason why it's squeezing. So when this is kind of the Lamb-Dicke barrier, so to say, where you were. So that's the optical potential. If you're doing here, everything is linear. Wonderful, everything is linear, but here you have less force. You have even negative force, and it doesn't work any longer at this range. So you can at maximum go from here to here, but if you come into the border, it starts already to squeeze, because it's no longer a linear slope. The linear slope is, of course, what would drive the coherent motion further, but then it stops here and comes to push against this area, and then becomes squeezed, and phase becomes uncertain, more uncertain. So that is where the engine kind of has to stop, okay? And so we can determine this extractable work. And what we see also, that this machine starts from fluctuations noise. It is really very noisy in operation. So it is quantum thermodynamics is not helpful for the engine here in that sense, so to say. It is a lot of noise, yeah, because the spin is prepared in spin up down, and basically the spin projection noise is very, very visible in our engine. Yeah? Yeah. It happens in the first moment of optical pumping, that you decide on spin up and spin down, and then this gives you random kicks, of course, a lot of random kicks, yeah, which increase the noise. Average, it does some work.
Quick question, what does the squeezing parameter zeta that you have depend on?
Well, you see here that is how that, on what does it depend? Wait a moment. Yeah, here, yeah, this is, if I go back, wait a moment. Go back is here. Here. So this was a simplified version of the optical force. You see, it is just depending on the spin. But in reality, if I go back further, I think I have it somewhere, hopefully. It's also here, but it is not linear, okay? It is not dependent on X and sigma in this fashion. It becomes here at this corners, there are other terms appearing.
So there's some parametric coupling in.
Yes,
that,
yes,
because
yes,
what is
absolutely.
Giving.
And
like-
that is what we conjecture for as the reason for this squeezing effect also. Yeah. Yeah. Because it appears when we come to this range where we are close to the border. So what you would like to do, you would like to have this periodicity not 280, but maybe 2.8 millimeter. So then you can operate this much larger, on a much larger oscillation amplitude. But then the force is also becoming smaller. That's also not nice. So that is now what I have in mind for the future. To go on with this, okay? And so far we had the working ion was doing everything. The working ion was doing somehow the reservoir when it was pumped in its spin up and down. It had a big role. This one ion had to take all the load. So it was the reservoir which was optical pumped in spin states, but it was also the object which was moving. So there's a lot of things which happen to this at the same time. Maybe you can make it easier when you have some ions which are playing the cold reservoir, some are hot reservoir, and you can reset them, and then you can operate a working ion which you bring here close to this, then make a gate operation, a fractional gate, then bring it over, make a fractional gate, and work on this spin only. So that is then totally a spin engine, which is no longer running on oscillation modes, but looking more like a quantum computer. You have a sort of very polarized spins here, which are cold, and unpolarized spins, and then you're going from with a working ion with its own spin to this, make a fractional gate, go back, make a fractional gate, go back and forth all the time. And this way you will exchange heat from hot to cold reservoir, and in the same moment you will basically turn your spin slowly of the working. And this spin can be then again digested, this energy in the spin can be digested by another ion, an auxiliary ion, which you swap the spin over from time to time as a load. So that is then more separated roles and more clear, I think, what you are doing really in an engine. So that is what I have in mind. And now that was my talk. Thank you. Yeah.
I often hear experiments, let's say they cool a system to ground states. Except that that's inconsistent with the third law of thermodynamics. So do you,
Yes,
is it just a shorthand?
yes, of course. Well, there is of course some limits to this ground state cooling, and it's very simple, actually. You can never cool the ground state, yes. And people are hopefully aware that this is true, but if we have, I plot my letters here of so let's say we have a two-level system. This is the electronic ground state with the electronic excited state. And this is now n equals 0 phonons. And here we want to end n equals 1, n equals 2, and so on. And what you do is you put the red side. That's what you want. So starting with the population here, you excite into that's the red sideband. And you exciting here, and then you are trusting to the spontaneous decay here, which brings you down here. So that's the first thing which is not right, is that this spontaneous decay can also bring you back here. Okay, it can also bring you here. These are all possible pathways. This here is reduced by a factor of 8. This is also reduced by a factor of 8. So they are smaller, these probabilities, yes, but they are existing. Now the red sideband, however, can also, you only choose the frequency. So you can also think that this red sideband would be off resonant exciting the excited state here. This is of course prohibited by the tuning here, but that's not infinite. So we have a certain chance that it goes here. And then it is cannot again scatter here to this phonon number n equals 3 even. So there is a heating effect. This is reduced by eta. And this can also happen. It can cool it and it can fall down. And if you now take all the terms, then you see there are never infinite line width here. So you have always some detuning and some off-resonant excitation. And you have always some diffusion because of eta. And if you now plot the whole thing, suppose you are almost in the ground state, almost say that was the why do we do perfect ground state cooling? We now concentrate on our level n equals 0. And we have just these levels left, okay? Say that is the end. And we're doing this here. Now there is this, that's the process which we love, but there is a certain process here which is reduced by eta, can also happen, okay? And this one can also happen. And if you plot this ones or this ones, then you get a limited amount of ground state. And what people do is you want to tailor the line width here, the gamma of this transition. Because if the gamma is very small against the omega, that's omega, then you are very slow in cooling, yeah, because it takes so long until you get a spontaneous decay. But then you can selectively be much more cold. So it's a kind of a, you can balance. You want to cool fast or you want to cool down. That's exactly the law which we know from thermodynamics. So it's absolutely reproduced here. Yeah.
And the sideband laser also stimulate them?
Pardon?
Can this sideband laser also stimulate the spontaneous decay? The one that is reduced by eta.
Well, stimulated emission means the recoil is taking exactly in this direction, and I think it is.
I see. So it would be off resonance.
Yeah.
Yes. Other questions? There's time. Beautiful lecture. I think, experiments are always necessary to keep the theorists honest. Yes.
Yes, but the theory is very important to keep the pressure on the experiment.
Yeah, it works both ways, but
That
that's
is
not-
even more important. I feel like this is more like the other way around.
You need also accomplished experiments
Yes.
too.
Yes, absolutely. But I'm coming to this point. I want to change the whole situation a bit by making the experiments accessible online for theory people, okay? Not only one computer where you can dial in and program your Python code and run the gate sequence and not knowing anything about trapped ions and all these kind of things. You just run your Python script and Qiskit or whatever you like. But it doesn't exist for the spin boson situation. And there I want also to make it such that you can dial in your detunings, your laser cooling settings and so on and do your own experiments. And for example, if she wants to know what's the cooling limit, then she can vary the detune the Rabi frequency and check what's the limit and verify the law. Okay,
Fantastic.
thank you.
Thank you.